All right, we've got a theorem next, and this theorem just tells us two really nice things. It's easy enough to prove. I'll prove it very quickly. So for k and c real numbers, remember that's, if you haven't seen this notation, this just means negative infinity to infinity, i.e. all real numbers when you see it. So in your head you can just replace that symbol with all real numbers. So when we say that c and k are, this symbol here means in or a member of. So if k and c are in the set of all real numbers, that just means k and c are just two real numbers. Okay, so for part A here, if k is just some real number, so insert your favorite real number, the limit of a real number, as x goes to any other real number, is just k. Graphically, what does the graph of a constant look like? So if y equals k, and I just arbitrarily assume that k is a positive number just so I can sketch the graph of k in a consistent manner, well, no matter where c is on the x-axis, if c is here or c is here, this y value is always the same. Another way to think about it here, a limit is a way of checking if this thing here changes its value based on this value, this variable down here. Does k depend on x? No, there's no x's embedded within k. K is simply a real number. K is independent of the value of x. So it's clear that if it's independent, the value of x doesn't affect the value of k. So the limit of k, as x does anything, is just k. Okay? Sorry. So the next thing, for part B, we have the limit as x goes to c of x. Well, think about what does the graph of x look like. Well, if we graph x, x is the y equals x, x is just the identity function. Or I had a professor at one point describe it to me as f of x equals x is just the idiot function. You just plug in whatever you want and it just repeats right back what you said to it. Plug in 2, spits out 2. Plug in 3, spits out 3. So it's no surprise that if we take the limit of x as x goes to c, the limit's just going to be c.